Okay, so what on earth is going on here? Okay, this gigantic mess right here is what happens when you try to evaluate something even as little as epsilon 2. And epsilon 2 is quite large, but it's pretty small considering we went all the way up to like zeta naught and the limit of zeta naught, etc. So this is just the very beginning of the deconstruction of epsilon 2. So it turns into a huge, gigantic mess. You have to start using rules of exponentiation. You have to keep track of where all your exponents are, and it gets really crazy. And this guy, he hung himself because he tried doing this, and now he's sad. So a much better way of doing this is with Veblen functions. And right over here on the side here, this might look a little bit complicated, but in the end it'll make you happy, because it's a much better way of doing things than this. It's a lot neater. So, first off, I'm going to erase this mess right here. And we're going to find a better way of evaluating things like epsilon 2 and upwards to much larger ordinals. So on the right-hand side, I'm going to keep that over there, because those are our rules for the Veblen function. We're going to need those. So I'll just write that down just so we know what we're doing. So this is Veblen functions. So basically this is a way of writing down our function, similar to the one that I wrote down here, this giant mess, but it's a much neater way of doing it. So let's start off at the very beginning of Veblen functions. So as you'll see, this it's kind of similar to the fast-growing hierarchy in that there's a subscript right here, and there's an input to the function. So it starts out very simple. This is the Greek letter phi. So phi sub 0 of 0 is just defined as 1. So very simple. As we move upward, phi sub 0 of a is just omega and exponentiation. So we're going to have omega to the power of whatever we put in the input here. So if we wanted to write down things that we've already done before, so you can do like, if we plug it into the fast-growing hierarchy, you can put like f phi sub 0 of 3, and then you have that of 3 in the fast-growing hierarchy. This would just be f omega cubed of 3. And that's something we've seen already. So you can kind of plug this into the fast-growing hierarchy exactly the same as you would the omegas or the epsilons or anything like that. But the usefulness of this comes when we start using our rules here to break things apart. So let's move on to our next function right here. So phi 1 of a is our epsilon numbers here. So let's start really simple. Let's try phi 1 of 0. So this would be epsilon 0 or epsilon naught, and that's our first fixed point of the infinite ordinals. So let's try that out and see what happens. Okay, so a lot of times I'm not always going to plug this into the fast-growing hierarchy to evaluate them. Like if I want to do diagonalization without the fast-growing hierarchy, you're going to see me do stuff like this basically. So let's say I wanted to evaluate this, or just break this apart. I might use square brackets. So basically, this is also diagonalization. I just use the square brackets to differentiate this, so you know that this is different than this, because you start getting brackets in here and brackets over here, and it starts getting a little bit confusing. So when I have the square brackets here, it's kind of like, it's the same as diagonalization in the fast-growing hierarchy thing, but you don't have to put the fast-growing hierarchy here, because we're not really trying to evaluate it right now. We're just trying to break it down. Okay, so this is equivalent to epsilon naught, as you can see here. Basically, this phi 1 of a is the epsilon series here. So if we put a 0 here, this is going to be epsilon naught. So this is just another way of writing epsilon naught. So if we diagonalize this, we should get our function that we got before. Remember when we put f epsilon 0 of 3? We diagonalized this and we got a f omega to the omega, whatever. So we should get the same thing. So we're going to do that. So following our rules here, that is this one here. So what we need to do, what this means here, is we take this many copies of the previous phi function. So you can see it's very much like the fast-growing hierarchy in that you minus 1 from the subscript right here, and you do this many copies of the function. So very similar to the fast-growing hierarchy. There's a few differences, but we'll go over those in time. So this is going to turn into 3 copies of the 0th function of phi of 0. And another way of writing that, I'm just going to put up 3 just so we know we're diagonalizing. And another way of writing that, same ways you could write in the fast-growing hierarchy, is phi of 0 of phi of 0 of phi of 0 of 0. Okay, so now we can figure this out from our rules up here. So phi 0 of 0, as we know, is just 1. So we're going to cross it off and just put a 1 here. Phi of 0 of 1, we can use this rule here. Well, what happens when you plug a 1 into the omega slot here? That's just going to be omega to the power of 1, which is just omega. So we're going to write out omega here. And now phi 0 of omega, that's again omega and exponentiation, and you're allowed to put an omega in this slot here. So this is going to be omega to the omega. So that's this here. And if you recall before, I was going to explain why epsilon naught, when you diagonalize, it turns into a tower of omegas n minus 1 instead of n. Well, this is where this comes in. This is the Veblen function that proves that, basically. Is because this turns into a 1. So this, when you put this in the top of here, or whatever, it really turns into nothing. And you're just left with 2 omegas instead of 3. And this would be the same if you plugged 4 or 5 into here. You'd end up, if you plugged a 4 into here, you'd end up with a tower of 3 omegas, because you'd have another phi 0 tacked in the beginning here, and 5, you'd end up with a tower of 4. So it's just another way of expanding out and diagonalizing epsilon naught in this case. Okay, so let's do an example with epsilon 1. So how you'd write epsilon 1 in Veblen notation, very, very simple, would just be phi 1 of 1. And you can see that from this equation here, phi 1 of a is e to the a, so phi 1 to the 1 is going to be epsilon 1. So this would be another way of writing epsilon 1. So if we plug this in and diagonalize it to 3, we can see why epsilon 1 turns into 3 omegas with epsilon naught plus 1 at the top. We can evaluate this. So first thing we're going to do is we're going to use another rule here, and that's this one here. Now this is a little bit different. It seems a little bit more complicated, and it kind of is, and this is really where it differs from the fast-growing hierarchy. What we're going to do is we're going to take 3 copies of the previous phi function like before. So we're going to go 3 copies of phi sub 0. But now what we're going to do is we're going to keep this function and write it down again. So we're going to have phi sub 1, and then we're going to take this number here, minus 1, which is a 0. And then we're going to tack on a plus 1 after the function. So this seems a little strange, and you might wonder where this is coming from. But basically, Veblen function has built within it a way to escape the fixed point trap. And the fixed point trap is that thing where you have omega to the a is equal to a. So you have the function kind of collapsing in on itself. Like if you remember, w to the epsilon naught is equal to epsilon naught. What is it? Epsilon sub zeta naught is just equal to zeta naught. You have stuff like that. Functions collapsing on themselves. So this is to create that plus 1 to escape that and create bigger ordinals. So they kind of just stuck that in there. So what happens when we evaluate this? So let's just plug in values for this now. We know that phi sub 1 of 0 is equal to epsilon naught. So let's plug that in, epsilon naught. And we know that this is going to be omega in exponentiation, 3 copies of that. So it's going to be omega to the power of this, another omega to the power of that, and another omega to the power of that. So what we're going to end up with is omega to the power of omega to the power of omega to the epsilon naught plus 1. And if you recall, this is exactly what we got when we plugged epsilon 1 into the fast-growing hierarchy diagonalized to 3. So as you can see, this is exactly the same as the stuff we were doing before. It's just a different way of writing it. It's a more systematic way of doing it. And you might be able to do it either way when it's stuff like epsilon naught. But as you saw before at the beginning of the video when I had this like giant mess written down here, this notation here becomes very, very cumbersome, and it becomes much more, it becomes a lot better to write it in Veblen notation. So let's just do a couple more examples. Let's see. What if I were to have let's say phi 2 of 1. You diagonalize that to 3. Okay, let's do the same thing as before. So this time we're going to take 3 copies of the previous phi function, which is phi 1, and do 3 copies. Sorry, I'm trying really hard now to keep my hand out of the way, because I watched all the previous videos at once and I could hear myself like yelling at the TV. I'm like, get your hand out of the way, whatever, because I'm trying to explain something and my hand is covering it. So trying really hard to do that. And also I apologize for the focusing issues. I'm doing this on my phone, and every once in a while it kind of goes like, But the ones that I watched, whatever, it didn't really blur out anything too important. So I think it should be fine. But once again, I apologize for that. Technical difficulties and whatnot. Okay, so anyways, we do 3 copies of the previous phi function. So we have phi 2 here. So we're going to do 3 copies of phi 1. And then we're going to keep this function here. So phi 2 minus 1 from the inside. And then add 1 to the outside to escape the fixed point trap. And then that's still diagonalized to 3. Okay, so what is this? Well, phi 2 of 0 is the zeta function. So phi 2 of a is going to be zeta a. So phi 2 of 0 is going to be zeta naught. So we can write that down. Let's see, sorry. Zeta naught. What about this? Phi 1 is the same as epsilon. So another way of writing 3 phi 1 functions is epsilon sub epsilon sub epsilon. So this is going to be epsilon sub epsilon of zeta naught plus 1, which, if you recall, is our evaluation of the zeta naught function diagonalized to 3 in the fast ring hierarchy. Again, this is just another way of writing it. Sorry, this kind of looks like a zeta.